So, what negative angle is going to be coterminal to 45 degrees? How did I get that so quickly? Exactly right. So what Ann says is that I can find another angle coterminal to any angle by adding or subtracting multiples of 360. So for example here, I took 45 and I subtracted 360 from it, and that's going to give me a coterminal angle. The idea here is if I'm starting at 45 and I take, I went the other direction though. If I turn negative 360 degrees, I'm going to end up right back where I started. Everybody agree with that? So again, if I take some angle x and I want to find things coterminal to it, I can just add or subtract multiples of 360 until my heart's content, right? Likewise, I can use this idea to check if two angles are coterminal. So for example, our 30 degrees and negative 690 degrees coterminal. So what I can do is I can say, does 30 equal 30 plus 360k? So if I solve for k, I'm sorry, there should be negative 690. There you go. If I take this equation and solve for k, if I get an integer value, I would say yes, they are coterminal. If I get a decimal, no, they would not be coterminal. So if we subtract 30 from both sides, and then divide by 360, I get k is negative 2. Since that's an integer, I can say that these are coterminal. Again, remember the notation here. This symbol means is a member of the set. This is the symbol for the set of integers. So what I've just said there is that because I got a value that's an integer when I solve for k, I know that they are coterminal because the criteria we set out before requires us to have a whole number multiple of 360. Positive or negative number is fine. What about if I ask you instead to find two angles coterminal to pi over 3. How does what we've done above change if we're talking about radians rather than degrees? Exactly right. So instead of talking about 360, adding or subtracting, we're talking about 2 pi's. Okay? So I could do pi over 3 plus 2 pi, and then I could do pi over 3 plus 4 pi. Maybe I should write it as 2 times 2 pi. It's maybe a little bit more clear as to what I did there. So to do this, I would need to find a common denominator and add these fractions. Oops. So pi over 3 plus 6 pi over 3 gives me 7 pi over 3. And then pi over 3 plus 4 pi. If I make a common denominator then, pi over 3 plus 12 pi over 3. So I get 13 pi over 3. Everybody okay with what we did there? Because you had to add fractions?
No, not on the
How I got what? Those things?
Yeah.
So I used this idea, or maybe I should probably say this idea, but I know that radians, 360 or degrees is the same as 2 pi radians. So I just abridged this formula with 2 pi instead of 360. So I chose k to be 1, and I did pi over 3 plus 2 pi, and then chose k to be 2, and did pi over 3 plus 2 times 2 pi.
Okay.
You could have picked any value for any integer value for k. I just chose 1 and 2 because they were small numbers, and I didn't want this to get overwhelmingly huge. Could you have picked -1 and -2? Sure. That's fine. So try this, just on your own right now, in your notebook. We'll go through it in like a minute, but are 47 degrees and -1,753 degrees coterminal angles? Just try this in your notebook. You'll probably need a calculator. Those numbers are a bit on the big side, so if you're not quite sure about the division, that's perfectly reasonable place to be at, because All right. For the first one here, what did you guys find? Yes. Good. So if you said the way to set this up is this, if I subtract 47 from both sides, and if I divide both sides by 360, I get that k is -5. And since that's an integer, I can say, yes, they are coterminal. Try this one. Is pi over 5 and 16 pi over 5, are these coterminal? David says they're not. That's correct. Good. So we'll start by subtracting pi over 5 from both sides. Oops. When I do that, I notice immediately this reduces. And when I divide both sides by 2 pi, I get 1.5. So we'd say, no, they're not coterminal. Everybody okay here? Correct. K needs to be an integer to say that it's not a member of. Yep. Depends on what kind of angle measure you're given. Since I was given one in radians, I used 2 pi. If I was given one in degrees, I'd use 360. That's all. Okay. Do we feel reasonably comfortable about coterminal and these angles of rotation? Okay. Well, we can't really get to the good stuff until we've kind of built out these definitions. You know, like what we're doing, like we're actually doing real problems and not just like building out concepts. You know, like right now we're starting with what we had in geometry and trying to build this out until we have a more useful system that can do things other than write triangles. And we just, right now we're just kind of building that out, extending those definitions. Joanna, do you have a question or are you stretching? Okay. Okay. So, in the last section, we said, okay, I can now embed an angle in the xy axis and really now define an angle of any size, right? We can define things that are greater than 360. We can define things that are less than 0. It doesn't matter. We can define kind of any angle we'd like, right? So let's say here's our initial side. Here's our terminal side. And I'm going to call this point P and say that it's some point on this angle. And I'm going to call this angle alpha. So that's the Greek letter alpha. It looks like the Jesus fish. And well, I'm trying to give you guys a frame of reference for what it looks like. It's maybe the first time you're seeing the Greek letter alpha. Many of you have seen the Jesus fish before and are like, oh, okay, that's how I draw that. So I'm just trying to be helpful.
And then the circle with the line through it, that's theta.
Correct. All right. All right. Shh. Yes, Anthony. Stop talking, please. So what we're going to do here is if I take any point on this initial side, I can drop a perpendicular back down to the x-axis. So what I've created here is a right triangle. Can everybody see that? What is this side of our right triangle? How long is that? It's x long, right? Because our point is x over. How long is this? Y. How long is the hypotenuse? It's the square root of x squared plus y squared. Why is it that? It's just exactly. It's just the Pythagorean theorem. So, if I have this definition, then I can define sine, cosine, tangent, cosecant, secant, and cotangent, all in terms of this point P. So sine is then going to be y over r. Cosine is x over r. Tangent is y over x. Cosecant is r over y. Secant is r over x. And cotangent is x over y. Is everybody clear as to how I did that? I just used our old right triangle definitions. But now, notice that these ratios are no longer related directly to side lengths of a right triangle. These are coordinates of a point on the terminal side of our angle. Does everybody see that? So we've translated from a very specific right triangle only definition into a point definition, where these are now defined using some point on the terminal side of our right triangle. And notice I used r as the square root of x squared plus y squared because it was a lot to write, so I just called it r. Okay. So let's do one little example of this, and then we're going to stop. I thought you'd enjoy that. So the point negative 3, 4 lies on the terminal side of some angle theta. Let's find the values of all 6 ratios for theta. So if I start with sine theta, I know that sine theta is y over r. Well, I know what y is. That's 4. What do I need? How am I going to find r? Pythagorean theorem. So I know that that is negative 3 squared plus 4 squared, which is 5. Okay. Cosine then is going to be negative 3 over 5. Tangent is going to be negative 4/3. Cosecant is going to be 5 over 4. Secant is going to be negative 5/3. And cotangent is going to be negative 3/4. Everybody happy with that? So one big takeaway right away, what do you notice about these ratios? Some of them can be negative, right? This was not possible using our old definition because we were stuck to lengths, which are always positive. Here, since we've extended our definition to move away from a right triangle into a point on the xy plane, we can certainly have negative values. So that's one immediate consequence. Let's stop here.